Lalit Singh sir, good morning sir. Welcome for the session. Dr. Lalit sir, good morning sir.
Yeah, good morning, madam.
So within 1 minute, 1 or 2 minutes, we will start the session, sir.
Yeah.
Thank you, sir. So distinguished officials, renowned individuals, excellent visitors, faculty members, professors from numerous engineering institutions, students, good morning everybody. Best wishes for the day. So it gives me a great joy and happy to invite you all for this today's morning. I, Krishnaveni, Assistant Professor from Department of ECS, KLEF, are delighted to invite you all for this online FTP on research perspectives on AI, ML, data science, and IoT. So it's planned for 3 weeks from May 17th to June 5th. We almost end of the second week. In continuation with that, we planned a short-term training program for the faculty and the research fellows in the areas of AI, deep learning, practitioner approaches from June 7th to till June 19th. So the objective of this FDP and STTP is to present researchers with the learning and multidisciplinary forums to learn about the latest breakthroughs, trends, and practical issues and aspects of the researchers and how it went on ICA, ML, and data science IoT. Alongside of regular teaching and research education affairs, partner in increased trend among the older universities, we feel proud and honored to invite today's resource person, Dr. Lalit Singh. He's a professor and PhD holder from IIT Bhubaneswar and scientist, NPCIL, BARC Department of Atomic Energy, Government of India. I take my privilege to introduce Dr. Lalit Singh sir with a few words. Dr. Lalit Kumar Singh is a scientist in reactor safety analysis, probabilistic safety analysis section of Department of Atomic Energy, Government of India since 20 years and has distinguished of working of pressurized heavy water reactors and water reactors in LWR and PHWR segments. His assignments over the years range from design, development, testing for fourth and fifth related researches and site validation of safety critical computer-based systems in Indian nuclear power plants. He also a faculty and the trainee in Nuclear Training Center. He gave a guest talk on our first day of this FDP program in the topic Deep Thinking of Safety Analysis and Safety Critical Systems. He is again back to enlighten us and share his knowledge today's session. I warmly welcome Dr. Lalit Singh, sir, for the today's session to associate the participants. Thanking you, sir. We welcome you for this FDP today's session, sir. Lalit, sir.
Hello. Yeah. Am I audible?
Yes, sir. You are audible now.
Yeah. Yeah. Thank you, ma'am, for introduction. And once again, good morning to all of you. And so today, in the last time, in my last session, I discussed about the safety analysis using data science and how you can perform the safety analysis. And we have discussed the mathematical formalism known as Petri Net. And we had also discussed like these Petri Net formalism is a very good mathematical formalism to know several insights about the system. And it is very important, especially when we are dealing with safety critical systems or control systems of some critical applications that include like aerospace or nuclear energy or medical domain, these kind of domains. So today we will be using the same mathematical formalism, and we will see like how we can go for the reliability prediction of the safety critical system. Now there is a important concept known as prediction and estimation. Estimation is generally based on your observation data. When you do have some set of observations, you can go for the estimation based on the observed values or based on the computed values. Now, estimation is fine when, of course, like, to gain the confidence on the reviewers or on the regulators. But as a system analyst or as a system designer, it is your responsibility, especially when we are dealing with safety critical systems that we have already discussed in the last session. It is your responsibility to ensure the reliability during the design phase itself. The reason behind is we all know the system development life cycle, and that includes broadly 5 phases. That is system requirement specification, where you have to collect all the requirements, and there is a systematic mechanism through which we can compile the requirements after discussing the peer review or after going through the system requirements specification. And mostly, if you look into the software kind of projects, the software errors stimulate from the requirement phase itself. So if you look like the various, the basic causes of the failure of the software, that includes that fails because of the requirements error or because of the design error. So we have to be very cautious while framing our requirements, and there are systematic methods through which we can formalize the requirements. For example, using the formal verification methods or the cause effect graphing, and these definitely these are these we have to formulate the system requirements very systematically when we are dealing with the safety critical systems, because
Sir,
if you see the system, yeah.
sorry to disturb you, sir. You can share your screen if you would like. You are a presenter.
Yeah. Yeah. I'll share my screen. Just
Sure, sir. Yes, sir. Thank you.
actually, I was just giving the overview, so I thought let me first finish the overview.
Yeah, thought
Then I
of the
can share.
same, but a few participants feel that they are not sharing. Yeah.
Yeah.
Thank you.
Thank you.
Thank you, sir. Your
So,
slides are sharing
so
now.
yeah. So basically, so generally, if you see the software requirements and design used to take like 30% of the effort. So sorry, 40% of the effort, and 40% of the effort needs to be go for the testing. That is 80%, and 20% is for the implementation. That's why we have to give a lot of time during the design phase, and a lot of validation checks has to be done during the design phase itself. So it would be very good if we are able to predict somehow the reliability during the design phase itself, because and it will give it will benefit us in many folds. First of all, we'll be able to meet the deadline, because if in the testing phase we come to know like our design is not so perfect and it is not meeting the reliability targets, then we may have to redesign, and we have to reiterate all the soft system development life cycle phases, and that again that will take the substantial time, and which can slip our schedule. And another benefit is if we are able to uh, during the prediction, if we are able to see like the end product will not be able to meet the objectives of the reliability, we may take the design decisions, and accordingly the advanced decisions can be taken. So here in this session we'll be discussing how we can predict the reliability, or how we can perform the reliability of the safety critical systems using artificial intelligence. So if first let me go through the reliability. What is reliability? What does reliability mean? So reliability is nothing but it is a probability of a failure-free operation of a system up to a given period of time under certain environmental conditions. Now, this definition is very important, and each and every term is very important. So first, I said reliability is a probability. It means if I'm talking with respect to the quantification of the reliability, its value will range from 0 to 1, because we know that probability ranges from 0 to 1. And 0 probability means it is the least reliable, and probability 1 means it is the maximum reliability. Theoretically, although any system can have the value of 0 and 1, but practically no system will have the value absolute 0 or absolute 1 of the reliability. It ranges between these, right? So, and coming back to my definition, so first it is a probability of the failure-free operation, means success operation of the system up to given period of time. Here, time is very important, because nothing is reliable for the infinite period of time. If I'm talking that it is reliable, I'll have to say up to what period of time I'm talking about. For example, you may be having a lot of friends in your childhood, and one or two maybe very fast friend, and you would have a thought like these friends are going to remain forever throughout the life. But you can see as an when your situation changes, your dynamics changes, your current scenarios changes, you start making new friends, and it becomes like really a lot of time. Even you may not know, you would not be knowing like where your that particular friend is now. So what I mean to say, reliability always depend on the time. So when I talk that this product is reliable, I'll have to talk up to what period of time I'm talking about. So reliability is a function of time. First thing that we need to understand is. The second is coming back to the definition, probability, it is a probability of failure-free operation of any system up to given period of time under certain environmental conditions. Now, this is very important. It also depends on the environmental conditions. For example, suppose you go to the vendor to purchase a new refrigerator and you get a warranty period of 1 year. And when you come back with a refrigerator, and for example, we throw it from say 14-story building, and it can fall down and it can collapse. Now you cannot go back to the vendor and say, see, you have given the warranty period of 1 year. I want the replacement of this refrigerator. What he will say, your warranty has been voided because you have not met the operating conditions under which this product was supposed to be operated. So what I mean to say is reliability also depends on the operating conditions. It may be possible that the same product may be high reliable at under one operating conditions and may be less reliable under different operating conditions. So these two things are very important, and hence the dynamics of the system. We should understand any dynamical system that its dynamics keeps on changing, and when its dynamics keeps on changing, definitely its reliability keeps on changing, and there should be some mechanism which should be able to capture those dynamics. So we will discuss the mathematical representation of the reliability, and then we will discuss again we will go through the Petri Nets and modeling of the system, because maybe there may be some of the like participants who would not be able to understand the Petri Nets. So I will give a quick review of the Petri Nets with the help of example, because the same mathematical formalism will be I will be utilizing to predict the reliability. We will see what all the important properties of the Petri Nets and what are the various analysis techniques. And then I will propose a reliability prediction framework in which I will be discussing the various phases that the reliability prediction framework contains, and I will be taking a case study and I will be illustrating all these phases of the reliability prediction framework on the considered case studies, so that easily it can bring it into the practice. The interested people can bring it into the practice, and then we can conclude our session. So this I have already discussed, but let us see the mathematical representation of reliability. So let x be the random variable, and that represents the time to failure of a component. So it means up to x, my product was working, and at x time, the product is failed, the component is failed. Then how we can predict the reliability of the component at time t, which can be equal to probability that the value of this random variable must always be greater than t, where t is the target time. As I said, the reliability depends on the time, and it is a function of time. So you can say rxt. So it is a function of time, and x represents the time to failure. So definitely x must be greater than t because if x will be less than t, it means my component has failed before T time and it is not reliable at all. So X must be greater than T for the reliability of that particular component. And from the mathematical knowledge or fundamentals, we can write it is equal to 1 minus probability X is less than or equal to T. Now, what is probability X is less than or equal to T is? It means my product has failed before time T, which was my target time. So it is a failure probability. So it represents a failure probability. So we can write equal to 1 minus failure probability that I'm representing by fxt. So that is also a function of time. So what we can conclude is reliability is equal to 1 minus failure probability. So or we can write we can name it as unreliability also. So reliability is equal to 1 minus unreliability. So from the total probability law, always the sum of reliability and unreliability will be 1 because these both are probabilities, right? So are my slides changing? Are my slides changing?
Yes, sir.
Okay, thank you. So now let us have a look on the traditional methods on the reliability estimation. So one was the most popular model was reliability block diagram. And in the reliability block diagram, what we used to do, we try to decompose any system into its various components because a system is composed of several components. For example, there are only two components, sorry, C1 and C2 in a one system. And the reliability of C1 is R1 and suppose the reliability of C2 is R2. Now, if these two systems, if these two components are arranged in series, then the reliability of the overall system will be given by the series reliability formula. That is R1 into R2. Similarly, when the components are arranged in the parallel, we can make the use of the parallel reliability formula. So this is the block diagrams means you have to represent the layout of the constituent components of any particular system. Layout in the sense you have to show whether you have to show what are all the components and what are the layout of these components, whether they are arranged in series or parallel. Then you can assign the reliability of these components and then you can evaluate the reliability of the overall system by using the series and parallel combination formula. So now the next is similar methodology or similar technique are the reliability graphs. And the reliability graph model constructs of a set of nodes and edges. Edges are the directed arcs. So the nodes represent basically the link between the components. And arc represent the components in the system. So for example, if you are able to see this figure, the left figure is the reliability graph where A, B, C are the vertex and V1, V2, V3, V4, V5, these are the arcs and vertex basically represents the connection between components as according to the modeling construct and all the edges are represent the actual components. So the reliability graph can be easily transformed into the reliability block diagram, and the equivalent reliability block diagram of this reliability graph is shown in the right hand side. So you can see all the V's are represented by the components, which are 1, 2, 3, 4, 5, and all the vertex are representing the connectors between those components. And you can see now it has converted into the series and parallel combination. For example, the 1 and 4 are in series. So you can apply the reliability, you can calculate the reliability of this R1, and it will be R1 into R4 if I'm considering the reliability of the component 1 is R1 and of that component 4 is R4. Similarly, R2 into R5. And all these then 3 segments will be in parallel, where you can make the use of the parallel reliability solver. So we can estimate the reliability of the overall system by using the reliability graph as well. Now, the very prominent methodology or the model known as a fault tree model, which are basically being used in in almost every safety critical systems throughout the world, whether you can see like in the nuclear domain, or automobile domain, medical domain, space domain, military domain, railways domain. Everywhere you will be able to see like they are making the use of the fault tree. Let us see what fault tree model is. So basically it represents all the sequences of the individual component failures that can cause my system to fail. And it is in the tree-like structure. For example, suppose if I say the failure is my laptop is not working. Now this is an observation failure. Now I can deduce the events, the basic events, which are the root causes, until I reach to the very basic events that we cannot decompose. For example, the root cause of the cause of that my laptop is not working could be either the power supply failure, or could be the mechanical failure, or could be the electronic failure. So these 3 could be in OR condition, right? So we can use the OR gates and we can connect this. Now, what is the power supply failure? I will have to deduce the reason. So power supply failure, the root cause could be the power socket is not working. So that is one. The second root cause could be there is a loose connection, that is root 2, cause 2. The third one is wire is break in between. In this way, like we can try to find out all the root causes. And similarly, for example, if I say mechanical failure, that could be failure of the button. It is failing to press, or it is failing to release. So we have to identify the failure modes in the root causes, and then we can assign the probability of that particular root cause. For example, if I say the button failure, now from where you can assign the probability. So for that, there are a huge set of database. For example, military handbook. You can see like millions of data sets are available. And these data sets have been derived based on the experience, industrial experience across the globe, based on the designers' feedback, based on the testing, and they are basically used as a basic event probability. We can assign the probability of the failure, and then we can if those two events are in AND logic. For example, suppose if I say a human is not able to see. Now the reason could be his left eye is not working, his right eye and his right eye is not working. So the observation failure is human is not able to see. And the root causes are left eye is not working and right eye is not working. Here we cannot use OR because if OR will be using it means human can see. So we can assign the basic probability, failure probability. Let us say P1 for left eye is not working. P2 is for right eye is not working. Then the top level probability can be given by P1 into P2 in case of AND logic. If they could be in OR logic, then the top level probability will be P1 plus P2. And top level probability, basically it gives the failure probability, and we can see like that we have already seen in the equation that reliability is equal to 1 minus failure probability. So we can negate it by 1, and that will give you the reliability of that particular system. So this is in that way that like the fault tree is very important for analyzing the reliability, for evaluating the reliability. These are the prominent models that we have discussed, although there are many other models are also existing. But the basic drawback in these models are they are not smart enough. They are not capable to capture the dynamics of the system. And when we are talking about the smartness, you see like the machine learning or the artificial intelligence concept starts coming into the picture. We have to design some kind of intelligence, uh, you know, algorithm which can predict a lot of dynamics, and accordingly, you can predict the reliability. Because as I said, there is a huge database available where you can find the reliability of the basic event. But though it may be possible that that particular reliability may slightly differ with your system, because your system is running under different operating condition, and as I said, the reliability depends on the different operating conditions as well. So the model that we have looked so far, they are very quick and can be solved using fast algorithms, but they assume the stochastic independence between the system components. It means it is assumed like if component A is failed, it is assumed like it is failing because of its own logic. While it may be possible like it may be getting a wrong input from component B, and because of B, it has failed. So there is some stochastic independence between the system components. Now to reiterate, as I discussed in the first session, there are the two type of processes. One are the stochastic processes and one is the deterministic processes. And we have already seen the example just for the sake of completeness. Deterministic processes are those processes, the outcome of which can be 100% guaranteed. And the stochastic processes are those processes, the outcome of the system cannot be 100% guaranteed. Although you might have done a rigorous planning, but then also it is not 100% guaranteed. And hence, it is very much essential. We have already seen that the law of nature is a deterministic in nature, but even the human reliability is not deterministic in nature. So definitely the creation of all the human, all the human-made systems will have some kind of stochasticity in it. And hence, we have to assume the stochastic independence, we have to consider the stochastic dependence between the system components. So the traditional models are basically non-state space models. And in this, we have assumed like the failure or the repair of the component is not affected by another components or by the other components. And it can be analyzed based on the individual components and the information about the system structure. So if you want to model more complicated interactions between the components, we have to look into the other models that do have a capability to capture the dynamics of the system. And we have seen like state transition models, the Markov models, the Petri Net models. These are the models which has a capability to capture the dynamics of the system. And in the Markov model, and in under these models, the dependencies among the system components can be observed in practice. So now coming back to the Markov model, because we'll be using Markov concept also in our prediction framework. So Markov model are the most powerful tool for the reliability and safety analysis because it provide the modeling capabilities that can consider almost all the type of dependencies under different fault conditions or operating conditions. And it has a capability to detect the stochastic behavior of the process. So if you see the modeling construct, basically it contains the two basic constructs. One is known as state and one is known as the transition. Now, what does it mean? Basically, we in the state space models, rather than decomposing the system in the form of its components, we try to decompose the system in the form of its state. For example, if I consider the human reliability in the form, if I consider the behavior of the human in the form of states, for example, a human is running, sleeping, talking, walking. So any system comprises several states during its lifetime, and the states could be behavioral states and the failure states. Now, the behavioral states are the normal states. For example, as I said, the sleeping, eating, cooking. But if I say the the failure state, maybe if I confront some accident, so it is a failure state. So if I'm able to, in some way, if I'm able to find out the reliability of all the success states or all the normal states, and because those states are independent, we can sum up all those reliability. That will give the reliability of the overall system. The other way out, because generally we do have several success states, but failure states are very less. So the other way out, if I'm able to find out the probability of the failure or probability of the system being in failure states, and I can sum up those probabilities, it will give the failure state probability of that particular system, and then the reliability of that particular system can be equated by 1 minus failure state probability. That will give the reliability quantification. So coming back to the Markov model, definitely we'll touch upon this concept while we'll be discussing about framework. So coming back to our Markov model, so the crux is just try to decompose every system in the form of a state. So you'll have to identify the number of states, possible states of a system. And then we can try to find out in some way, like what is the probability that my system will be in success state. And I can sum up those probabilities to give the quantification figure of the success state. That will give the reliability of that particular system. So now the mathematically Markov chain, how it, let us see some of the mathematical concepts which we are going to use in our prediction framework. So for example, there are only two states, I and J, and in my system, and let Qij be the transition rate from state I to state J. Transition rate means the number of transitions per unit time from state I to state J. For example, I do have a defined transition rate. How many times I used to sleep in a day in 24 hours, and how many times I take breakfast or I take lunch or I talk to my friends, I do my work. I do have, and every human being may have a different defined states. So let basically, for example, in my system only there are the two states for simplification, and Qij be the transition rate from state I, and I can transit from one state to another state. If I'm suppose sleeping, I can transit to uh, standing, or I can transit to speaking, like this. So we can define this transition rate is equal to minus sum of all the other transition rate from that state to all the rest of the states, where j is equal to I to n. If we are considering the total states, number of states are n in that particular system, and I and j basically are two states, are two subsets, are the subset of those states uh, of a particular system. So this is a very important concept that we are going to use in our prediction framework. Now the next terminology is the generator matrix. And generator matrix is a matrix where in the rows we can define all the states. For example, there are n states, so 1, 2, 3, 4 up to n. In the column also we can define number of states, and then we can fill in the matrix with the transition rates from one state to another state. And that is known as the transition matrix. First, I'm discussing the terminology. How we can do that, we will be discussing. Okay. So this is that known as transition rate matrix, because it is containing all the transition rates from one state to another states in a system. Now coming to the Petri Nets, as we have already seen, Petri Nets is a graphical tool and it is a mathematical tool. And the concept was introduced by C.A. Petri in 1960s. And why graphical tool? Because you can model the requirements of the system graphically, and you can easily show to all the stakeholders, and it is very easy representation. So stakeholders may not be finding much problem to understand the model, and uh, it can benefit to all the stakeholders. For example, if I'm the uh, system designer and I have given, I have outsourced some project to any company, and he can model the requirements and he can show in the form of Petri Net to see where I can see the behavior of my system, and I can analyze whether all the requirements, all the function requirements have been captured or not. And there itself, if I find some lacuna, I can discuss and I can resolve. And so it is and similarly for the testing testers, where you can see like the behavior of the functional behavior of the system. So it can help the testers to design the test cases to test particular system. And it is a very good mathematical tool because we can use the state equations or the algebraic equations to know more and more insights about the system, and hence it's a very good communication mode between theoreticians and practitioners. So this was just let me go through the very quick review, although we have seen in our last presentation, but for the participants who could not understand, I'm trying to give a quick review. So the concept was introduced in 1962. Basically, the concept this of the Petri Nets was introduced to capture the stochastic behavior of the system, and the thesis, because he was a PhD scholar, and he proposed this. C.A. Petri was a PhD scholar who proposed this concept, and after going through the thesis, the MIT USA tried to explore the possibility whether this Petri net will be able to serve or model the concurrent systems and parallel computation, because there was an era in 1970 where the people were striving to develop the concurrent systems and parallel systems. And the conclusions were very good. And again, the people were trying to strengthen the model, and so they decided to meet after 5 years. Then again in 1975, MIT USA conducted a conference on Petri nets and related methods. And then it started getting introduced in the industries. And so because of the high demand in the industries, and they had to spare a lot of time to give the training to the new entrants. So the Germany started a course on the Petri nets, known as general course on general net theory of processes and systems, where the people will be able to do the model of will be able to model the system in the Petri nets. And so then later on, in 1980, the first European workshop was conducted by France, and the objective was to look into whether it is able to cater several other kind of applications, like control applications or safety critical applications, information applications, depending on the interest of those particular like industries. And in 1985, basically, then the people started strengthening the model capabilities. And for example, if you are dealing with the response, if you are dealing with the real-time system, definitely the response time of the system is important. And hence, your Petri net model should be able to embed this timing information. And with this objective, timed Petri net, a different kind of flavor of the Petri nets was introduced. Similarly, other Petri nets were introduced depending on the domain. So the first international workshop on the timed Petri nets was conducted by Italy in 1985. So although it is not an exhaustive list, but it brings out some of the important milestones just to and then just to have a feel the importance of this Petri net mathematical model. So again, I can explain. I'm for the convenience, I have taken the same example, where I'll be demonstrating the working mechanism of the Petri nets, and because the same concept I'll be utilizing to model my case study, and I'll have to basically then predict, I'll have to propose the framework where I'll be utilizing all these concepts. So suppose I want to model the basic chemical reaction, that is 2H2 plus O2 that gives the water. So now before going through the model, how we can model this particular chemical reaction, let us understand the basic modeling construct of this Petri Nets. So if you are able to see this figure, there is there are the three big circles known as the places. So basically, I'm representing these places for representing different elements, chemical elements. So, and the different chemical elements are hydrogen, oxygen, and water. So this place is representing hydrogen, and this place is representing oxygen, and this place is representing water. So there are the three places in this figure. Now the next is, you can see there is a rectangular block, is known as transition, and the transition and places can be connected by the directed arc. So if you see in this figure, there is only one transition T, and which are connected by all the three places. So hydrogen place is connecting with transition T, oxygen place is also connecting with transition T, and water place is also connecting with transition T. Now there is a concept of input arc and output arc. So the arc from which entity it is emerging is, for that particular entity, that arc is known as output arc. And where it is terminating, for that entity, it is known as input arc. So for example, in this figure, the hydrogen place is containing output arc, one output arc, because one arc is originating from here. Similarly, for oxygen place, there is one output arc, and for transition T, there are the two input arcs. One is coming from hydrogen and another is coming from oxygen. And one output arc which is connecting the water place. And similarly, for water place, there is only one input arc which is coming from transition. Now, the another construct is known as tokens. You can see the embedded circles inside the places, inside the hydrogen place and oxygen place. These embedded circles are known as tokens. And it depends on your particular context what you want to represent the tokens. But basically, tokens represent the dynamics of that system. So definitely the things which keeps on changing, you have to basically, you should represent this token. So you can see like hydrogen, because hydrogen contains two atoms. So I'm representing the token, the two tokens which are representing that hydrogen contains two tokens. Similarly, in the oxygen place, I have used the two tokens which are representing that oxygen atoms, because it contains two atoms. And Now there is the weight of the arc. You can see the numeric number that is assigned on all the arcs. So the arc which is connecting hydrogen place and transition T is having weight 2. And this weight basically represents, I will tell the significance of this weight. Just a moment. Yeah, hello. Yeah. So this weight base, the oxygen, the weight of the arc, which is connecting oxygen place and transition T, is 1. Although I have not mentioned any weight, but if I am not mentioning any weight, I have to, I should consider the weight 1. Or otherwise, the other way, I can write the weight numeric number 1 also. Similarly, the weight of the arc that is connecting transition T and water places. Now, let us see the working mechanism of this. Petri net. So this figure is basically representing the initial state of the system. And my system is this chemical reaction. This is my system. And its initial state is 2H2 plus O2. So this is representing the initial state of my system. And in the Petri nets, the states of the system can be represented by the distribution of the tokens among all the places. So you can see the distribution of the tokens are 2, 2, 0. Because the hydrogen place contains 2 tokens, oxygen place contains 2 tokens, water place contains 0 tokens. So 2, 2, 0 is the initial state of the system. And in Petri net terminology, the initial distribution of the token is also known as the initial marking. Generally, the distribution of the tokens in the Petri net is known as marking. So it is the initial marking, which is basically representing the initial state of the system. Now, we have to change the state of the system and it needs to be converted into the water. So definitely, as I said, the states are the tokens are basic states are the representation of the distribution of the tokens. So definitely the token movement will happen. The token distribution will change. And how the token distribution will change? The tokens can move from one place to another. And for that, the transition, any of the transition in your Petri net figure must be in a enabled condition. Now, so it means if I want to change the state of the system in this figure, my transition T must be in enabled condition. And what is the enabled criteria of the transition? All the input places must contain sufficient number of tokens. And all the input places means what are the places which are connected by its input arcs. And the output places or output transitions are what are the places or transitions which are connected by the output arc. So if you see in this figure, the transition T contains the 2 input places and it must contain sufficient number of tokens. So who will decide whether it contains sufficient number of tokens or no? So the weight of the arc will decide whether it contains the sufficient number of tokens or not. So weight of the arc that is connecting hydrogen place and transition T is 2. So hydrogen place must contain at least 2 number of tokens. And the weight of the arc that is connecting the oxygen place and transition T is 1. So oxygen place must contain at least one number of tokens. So I said all the input places. So these two are only the input places. So it fulfills the eligibility criteria. It means that T is in enable condition. And if T is in enable condition, it will fire. And when it will fire, the movement of the tokens from the input places to the output places occur. But there is a firing rule. How many number of tokens will be moved out from input places, and how many tokens will be deposited in the output places? Who will decide? That will again be decided by the weight of the respective input and output arcs. And the weight of the input arc, which is connecting the hydrogen places 2. So after firing T, the 2 tokens will be moved out. Similarly, the weight of the arc which is connecting oxygen place and transition T is 1. So the weight, so 1 token will be moved out. So although the 3 tokens will be moved out, but how will be deposited into the output place? Only that will also be governed by the weight of the output arc, and which is 2. So here in water place, only 2 tokens will be deposited. So the crux is, although in total the 3 tokens has been moved out, if you sum up the number of tokens in all the input places, only 2 tokens are deposited into the output place. Because so here there is no conservation of the tokens. The deposition, the movement of the token or the removal and deposition of the tokens will be depending on the weight of the respective arcs. So the next is, after firing the T, the 2 token has been moved out from the hydrogen place, 1 token has been moved out from oxygen place, and 2 has been deposited. Now let us try to see whether T is in now enable condition. No, it is not an enable condition, because what I said, all the input places must contain sufficient number of tokens. And here the hydrogen is not containing sufficient number of tokens, for which he should contain at least 2 number of tokens, as the weight of the connecting arc is 2. But oxygen is containing. So but it should be in AND logic, not in OR logic. So it means now my transition is in dead state. It can never be enabled. So it means this is the final state, because if my distribution of the tokens are not changing, so it means it is a final state. So it has now converted into the water. Now, coming to one important terminology known as reachability graph. And the reachability graph is basically the representation of all the possible number of states in that particular system. So if you can see here, it was the first state that is represented by 220, because the token distribution is a representation of the state. After firing T, it has the distribution of the token has now 0, 1, 2. So, and this is the final state. So these are the only 2 states. So this is known as reachability graph. You can write down the token distribution, then which transition was responsible to change the token distribution, and then write down the next token distribution. So it will help to identify a very important conclusion that we can draw over here is, it will help to identify the number of possible states of your system. throughout its operational life. So basically, it overcomes limitation of the Markov chain. In the Markov chain, we have to first identify the number of states. But if I am failing with the identification of number of states, then how can we do that? And this Petri net is not only helping the model to model, but also it's helping to find out all the possible number of states. So now any analysis techniques, the success of any model depends on the two factors. One is the modeling power, which we have already seen in the Petri net do have, and one is the decision power. Decision power means if it can bring out some of the important insights based on which we can take the design decisions. So now let us try to understand, before the case study, we will try to understand some of the preliminary concepts related to this framework. So let us see how we can represent the Markov chain mathematically. So suppose, as I said, Markov chain is a set of states and transitions between those states. So suppose it is a representation if you are able to see the figure. Suppose there are only two states, S1 and S2. So S1 can transit to S2 or S2 can transit to S1. This is a small representation. And how mathematically we can write the sequence? So suppose there are the sequence of random variables, X1, X2, X3, and so on. Then what does Markov property says? That the probability that my system is in any state will depend on its previous state and will not depend on more previous states. So for example, I want to find out the probability of my system is in n plus 1 state. It is x, so it will be only depending on previous state, that is xn, and not on more previous states. So if you say more previous states from 1 x1 is equal to x1, x2, x3, it will not depend on those states. So we can simply write that probability that my system will be in n plus 1 is equal to x, given the probability of my system was in state n. Okay, so this is the representation. Now, reachability graph, how we can make the reachability graph of which we have discussed. So suppose I have taken a very random example, and this is the marking which can be represented by M, and marking are the distribution of the tokens. Suppose there are the 7 places in a figure, and having a token distribution like this 1 0 0 1 0 1 0, and this token distribution now can be changed after firing T1 like this, after firing T2 like this, and similarly we can identify all the token distributions, possible token distributions, which are just representation of the possible number of states. So we can easily transform this reachability graph into the Markov chain. So this is nothing but it is a state. So it is just a state, and these are the states, and these are lambdas are the failure rates, okay, or the transition probabilities, you can say, between those states. So it is just a equivalent Markov chain. It means the Petri nets can also be converted into the Markov chain by drawing the reachability graph and then converting it into the Markov chain. Now, let us consider the reliability prediction framework and what are the various phases and how we can compute the reliability. So the first step is we have to create the Petri Net model. So we have already seen while discussing a chemical reaction how we could create the Petri Net model, and that Petri Net model can be converted into the Markov chain. And we have already seen how it can be converted into the Markov chain by converting into the reachability graph, and then reachability graph can be converted into the Markov chain, and then we can compute the reliability. We will see how we can do that. We are going to illustrate each and every phase on our case study. So phase 1 and 2 have already been discussed, and the phase 3 will be we will be discussing taking the case study. So before before that we have to understand some of the basic concepts that we are going to apply in our framework. So suppose let pi it be the probability that a system is in state I at time t, where I is equal to failure F1 to Fm and behavioral states. As I said, the states can be failure states and behavioral states. Now, the next statement is very important. As t goes to infinity, these probabilities converge to the stationary distribution. Stationary distribution means it will settle down. For example, you just take a water in a glass and you keep it on the table. You will see like at the initial time t is equal to 0, the water was zigzagging. And after some time, it will settle down. It will take a less time. Now, just consider the similar case. The water you are filling in a very huge tank, probably at the size of room. And suppose you are lifting that room with a crane and putting down somewhere on the ground after filling the water. You will see it will take a very long time to settle down. The water will take a very long time to settle down in this case. So what I mean to say is, as your system becomes more and more complex or large, it takes a longer time that all the state probabilities will converge into the stationary distribution. So theoretically, I write as time goes to infinity, all these state probabilities will converge to the stationary distribution, and which can be converted into by the following equations. So the first equation is very simple. It just tells the sum of all the probabilities of failure state or success states will always be equal to 1. That is from the total probability law that we all know. Now the second equation is very important and a little conceptual. I'll try to explain the concept. So consider the second case where you have filled the water in the very big container, for example, at the size of the room, and the water is zigzagging at the initial time t is equal to 0. So after delta t time, so suppose the initial state will be S0, let us say, but after delta t time, it will approach towards settling process, and let the next state will be S1. So S1 will be depending on S0, as well as the transition probability from S0 to S1. Similarly, further after S1, it will reach to S2, and S2 will again depend on the S1 and the transition probability from S1 to S2. So it is a kind of Markov chain basically, because the current state is depending on the present and on the previous state, or the next state is depending on the current state. So suppose now the water has been completely settled down and the final state is Sn. Then what will be the Sn plus 1 state? It has already been settled down. It is going to remain same, right? So Sn plus 1 is equal to Sn. But the equation will hold same. What was Sn plus 1 is equal to Sn into the transition probability from Sn to Sn plus 1. So this is what the second equation is, where the pi r is or the estimator, it's a pi estimator is which is the stationary distribution will be the same stationary distribution into the transition probability matrix, because I'm considering all the states. So we'll have to multiply by matrix, right? So we will be utilizing these two equations. Now let us take a case study of a, for example, communication module. And suppose the system architecture is like that. My safety critical system is an embedded system, and it is capturing the data from the field sensors, which are the real-time data that may be, I mean, representing the pressures, temperature of, or flow, these kind of variables. And it processes those parameters. It can contain the analog parameters as well digital parameter. Digital parameter probably the state of a device, like valve is open, close, pump is on, off, like this. So it can capture the current state through the sensors. It can process because every signal is transferred in the form of voltage or current, and it has to be converted into the engineering values. And after conversion, it is sending the value to the graphical user interface, and graphical user interface basically is representing the data into various formats to the operator for the convenience of our knowing the status of the system, the healthiness status of the system. And for this communication, definitely the communication module plays a very important role, because the data, if data will be corrupted, definitely the information will be wrong and it may hamper the safety. So I'm just taking a very small communication module as a case study. And first, let us see what is the protocol of this communication module. And the protocol is very simple. For example, if I want to call a friend, what I'll do, I lift up my phone, I'll dial his number and I will say hello after ringing when he lifts up. And then I will wait for the response. If I will not be able to get any response, I will again say hello. If I'm getting the response, I will assume, okay, now the connection has been established. But if I'm not able to get the response, I will keep on saying hello, hello periodically till I get the response. But for how much time? If suppose if I'm saying after 10 iterations also he is not responding, I will assume like the connection is lost. And I will cut the call and I will retry. And the same concept was designed in this communication module. So for example, there is an embedded unit which sends the new packet because the information is sent in the form of packets. Then the value of the count is set to 1. I have kept one variable known as count. It is set to 1. It will basically count how many number of packets have been transferred. Then the embedded unit waits for the acknowledgement after T1 after sending the packet. If embedded unit receives the acknowledgement before time T1, I will declare that packet send is successful, and I will keep a semaphore variable just as a flag. I will change the status of the flag to its complement. But if count is less than n, where n can be pre-decided how many number of tries I need to make, an acknowledgement is not being received, then the embedded unit retransmits the packet and set the count plus 1. Else the embedded unit terminates and send process unsuccessful. Where I will not be changing this semaphore variable. And if T1 elapsed after the last data sent, I will be destroying this semaphore variable. So let us try to model this case using Petri Net. And this is a Petri Net model. Let me explain how it has been modeled. So a place where you are able to see the tokens, basically in the two places that there are tokens. So a place known as PSRDY0. If the token is in this place, it will it represent like embedded units is ready to send the packet with the semaphore variable is equal to 0. And the other criteria, because initial criteria, you have to, that display unit must get a request from the embedded unit to send the data. So I have set initially both the token cells in these places. Next, the transition TS0. It represents the embedded unit sends the packet with sequence number 0 because every packet will be sending in the form of sequence. And it will set the count value by firing this transition. Then this place ESW0. It represents the embedded unit is waiting for acknowledgement with sequence number 0. So here it is waiting for the acknowledgement. And after it is not getting any response, suppose this STSW0, it represents like embedded unit has detected the timeout of the acknowledgement. And PT0 and 0 represents like embedded timer has been, acknowledgement timer is timed out for data sent. And then TS0K, this transition represents like embedded unit sends the packet with sequence number 0. And its transition is fired only when K is less than N. And we will increase the value of K. And here the PS0S will represent like data packet has been sent, and then it will go to the communication module. So TCOM1 is a transition that represents that the data, that the display unit sends the acknowledgement to the embedded unit with sequence number 0. And here, because this PR0 R1R, it represents the embed that the acknowledgement has been received, and it was waiting for the acknowledgement. So both the tokens will be moved out, and again it will be ready to send the new packet. Now the very interesting fact is that we have okay. Before that, if it is not unsuccessful, it is waiting, keep on waiting for the acknowledgement, and it is not unsuccessful. No, sorry, unsuccessful, which is represented by transition TS0 ACK as you see. Then it will, the token will move to this place PD as a U, which will represent like data send is unsuccessful, and it is reported to operator. Now, an interesting fact is that the left half is exactly the right half of this figure. And the reason is for the redundancy, I have put two embedded units and two graphical interface units so that because I'm dealing with a life critical system, in case of failure of one, I can, the redundant will be able to take. So one time I'm sending the packet from one embedded units, another time from other embedded units and display unit like this, so that it also ensures the online testability, which is a very important feature. Now let us try to evaluate reliability of that particular system. Now, here we have to, these are the time delay, we have to insert, we have to embed the transition delay of each of the transition. So these are the delays. Now from where these delays are coming? From the artificial intelligence algorithms. From the similar kind of systems, the artificial intelligence networks or the IoT networks, they are interacting with each other and they are analyzing that what should be the transition delay, what is the actual average transition delay. And they are not doing their linear interpolation, but they are using the Bayesian updates, which is which can be used for the artificial intelligence algorithms to extrapolate the data based on the predictions, basically. So it is these are those delays. And when you run this model in the tool, there are the various Petri Net tools like TimeNet, Petri. When you run in the TimeNet tool, you will get the throughput of each and every transition. These are the throughput values. Throughput means number of transitions per unit time. It is a firing rate of every transition. So it's a firing rate of all the transitions. Now, the next is we have to, first phase is complete. We have to now convert it, we have to create a reachability graph. And the reachability graph, for the reachability graph, we know we have to identify the token distribution after analyzing the every transition firings. And these are the token distributions, the total line distribution that we got. And these are the tangible because all the transitions do have a time delay. If they do not have the time delay, it will be the vanishing markings. Otherwise, it will be the tangible markings. And just for the sake of convenience, I have mapped lambda, all the lambdas to lambda 1 to lambda 12. Just for the sake of convenience, that's it. So this is the reachability graph creation, where all the markings have been shown, and we can easily convert it into the equivalent Markov chain. So here you can see we have shown the marking and the change in the marking along with the responsible transition through which the marking has been changed. So now you can see this reachability graph can be easily converted into a Markov chain. So these are the nothing but the states, and these are the lambdas, which are representation of a transition rate. Now we have to create a transition rate matrix, and we have already discussed what is transition rate matrix. It basically tells the transition rate of all the transitions, and we have also seen. So coming back to from M0 to M1 is lambda 1. So from M0 to M1 is lambda 1. And why this is minus lambda 1? From this equation, if you are able to recall, let me go back to that particular slide. From this equation. So the diagonal transition rates will be minus of summing of all the transitions. Yeah. Okay. So in this way, M1 is transiting to M2 and M4. So lambda 3 and lambda 1. So M1 is transiting to M2 and M4. Similarly, the diagonal transitions can be computed. And this is the transition rate matrix. Now, once you are able to find out the transition rate matrix, you will be able to estimate the transition probability, which is very simple. You have to just normalize the transition rates. So if I want to find out the probability, transition probability from state I to j, it is equal to the transition rate from I to j, and we'll have to normalize it. That means we'll have to sum up with all the transitions. For I is not equal to j, otherwise it will be 0. So this is the transition probability from one state to another state. Now, I will have to utilize those two equations. One is the sum of all the state probability will be 0. So all the M0 plus M1 up to M9 is equal to, 1. It will be equal to 1. And this is the equation that we have already discussed, which I have used here. So this is the final state. Previous state will also be remain same in the stationary distribution. And this is the transition probability matrix that we have already calculated. And then we can solve both of the equations, which will give the transition probability of each and every state. And now one interesting fact is that the M3 and M8, these two states are failure states, because here the acknowledgement was not sent successfully. So either we can sum up the state probabilities of M3 and M8 and we can negate it by 1, or we can sum up all the rest of the probabilities. So just for the reliability, to compute the reliability of the communication module, I have sum up the M3 and M8 probability and I have subtracted by 1. And this is the reliability of the communication module. So we can quantify the reliability of this communication module, and it will help me to take the decision whether I should have to change the design or whether this reliability is fulfilling my target reliability. So in this way, like you can, the crux is like we have seen like how this Petri Net is able to basically predict the reliability during the design phase. And if your system is very large, you can break down the system into the various functions and you can do the quantitative assessment for that particular system, and which will which will give a which will give a confidence to all the system designers that it is really performing, you know, uh, or it is meeting the reliability target. So that's all I wanted to discuss. And in case of any questions, I'll be happy to answer. You can ask any questions. Thank you.
Lalit sir, can we request some of the queries from the participants?
Yeah. Okay. It is in the chat box. What?
Yes, sir.
Or,
You.
or, or, or the or the participant can ask directly.
Yes, sir. Yes, sir. Participants, you can unmute yourself and you can raise your queries if you have any. Else, you can put it in a chat window so that we can convey to the Lalit sir. Lalit sir, there is a one question. What are the critical variables in Markov model for a prediction framework?
What are the critical variables in Markov model on the prediction framework? See, we have seen the Markov model. It contains only two things. One is the state, and second one is the state transition probabilities. So if you are talking about the parameters or variables, variables are only the state transition probabilities, because the state identification have already been done, which is a static in nature. Yes, the transition among the states, and the equivalent, the state transition probability can be derived by the, we have seen by the Petri Nets also, uh, how those transitions, the generator metrics basically that we have seen, that help us to derive that particular parameter.
Lalit sir, is there any case study available related to the Petri Nets in coordination with the IoT application development?
Yeah, there could be several case studies. IoT in IoT applications. For example, like you do have a system where your processing nodes are located in a different locations where those processing nodes are interacting with each other. And you can model the behavior of that in your Petri Nets. So you can find several case studies on the internet in the subsequent papers. Also, where there are a lot of papers also in Elsevier journal or IEEE transaction journals, which are based on the Petri Net and the case studies are IoT based case studies. So you can go through those case studies.
Yes, sir. Yeah, thank you so much, sir. And there is another question, state transition properties. One participant asking about the state transition properties.
There is no concept of state transition properties. It
Okay.
is not a physical phenomena. It is a dynamic variable basically, and
Yeah.
the state transition is the value of the state transition will be depending on your system dynamics basically. Okay, so as such, there is no state transition properties of such.
Yes, sir. So, any more questions from the participants? So, another question from the participant, can we define critical variables of Markov model using state transition matrix?
Critical variables. See, first of all, we should understand Markov model only one variable, that is the state transition probability. And state transition matrix, as I said, we have also seen also. I think the entire concept was around this only. How we have utilized the state transition matrix to compute the probability, state transition probability of the Markov chain. So yes, you can go back to my slides only. So the entire discussion, the most of the discussion was related to this, and we can use the state transition matrix to derive this state probability matrix. Okay. Why is it hidden Markov model? See, the hidden Markov model basically, first, it is not a hidden Markov model, first of all. Now, let me make you understand the concept of hidden Markov model. Hidden Markov model, it is a kind of black box where you are aware of only the inputs and outputs. What inputs you are giving and what output you are getting. You are not able to understand the behavioral characteristics or the internal working mechanism. Here, everything was very transparent. So, in the case, in your pardon, yeah. So in where there in the case you are given a system where only input and output are basically you are able to know, and you are being asked to analyze some of the critical properties, but you don't know the working mechanism. It's a kind of black box for you. So in that case, you can make the use of the hidden Markov models to derive some of the critical attributes. Now, what is the difference between decision tree and Markov model? First of all, we need to understand the tree. Tree is an hierarchical structure who has a parent and has a child, as you might have got in the data structure as well, right? There is no concept of parent and child in the Markov model. Parent and child only you can see like state transition. Yes, in what sense? If current state is not, you are not able to confront, the next state you will not be able to confront. Okay, so only that is the relationship, as we have said in the state equation also, the Markov state equation also. But the tree concept and the Markov model concept is in this way it is not related. Okay, next question is how to calculate the probability matrix for regular Markov chains. So, as I said, the probability matrix, there are the multiple ways. For example, you may have to use, you can use your artificial intelligence algorithms where you are having the similar kind of systems, and you can derive, you can extrapolate those that particular data, and accordingly you can calculate. You make the use of Bayesian or Kalman filter or other artificial intelligence algorithms where you can derive or extrapolate. Uh, Ultimately, the crux is you'll have to find the distribution of the data. So in what way you can find the distribution of the data based on the observation? So either you can make based on the, you can make your you can take the observation from the testing data or from the similar kind of projects. You can then extrapolate it by applying your design principles, by analyzing the operating conditions. Accordingly, you can make the use of the algorithms, and you can do that.
Namaste, sir. In uh, stock price prediction, sir, using hidden Markov model, probabilistic machine learning algorithm, sir. If the data is big data in streaming environment, and compared to other machine learning algorithms, the prediction accuracy will be in which algorithm will be more if we implement compared to other algorithms with respect to hidden Markov algorithms, sir, in probabilistic way of implementation.
I could not get your question. Can you please repeat? For example?
Yes, sir. Yes, sir.
Yeah, yeah.
Hidden Markov model is a statistical based probabilistic machine learning algorithm, sir, which is used for prediction of stock prices also, sir. And there are several other algorithms also there which we can implement for predicting the stock prices in machine learning algorithms, sir. Compared with other algorithms,
for prediction of
stock prices, sir.
Stock prices. Okay, okay.
Compared to other algorithms, how it is more better, or other algorithms are better in prediction accuracy, that how we can make it determine, and how we can implement it, sir, in real-time environment. If the data is big data in a live streaming environment.
See, the crux is when you are making any predictions, you have to rely on the statistical data. That is the first rule, right? The second rule is the sufficiency of the data. If you do have more number of data, the more accuracy will be there. The third one is the diversity of the data. The fourth one of the internal working mechanism or the design of that particular system. These are the important factors which you can basically make the use of deriving your algorithms. So definitely the hidden Markov model, as I said, they do have a limited power in the sense because you don't know the internal mechanism, and but you have to come out with some of the observation. So where you are lacking the data, you rely on the hidden Markov models because you don't know the internal transitions, how the transitions are taking, what are the internal states, you are not aware of. So as and when the transparencies are there, for example, if you are using the other machine learning algorithm which are able to analyze all these data. So for example, one way is the big data analysis because you are streaming the data at in one database and you are chunking out the data, you are trying to uh, filter out the informative data which can come out with your objective, and you have to then use that data. So it is not only the voluminous of the data, but also the useful data basically. So for that, you may have to use such kind of algorithms. Probably you may have to uh, design your own system which can do all this work for you, and definitely it will give you more accurate prediction.
Yes, sir. Thank you, sir.
Yeah, hello. Yeah.
So there is another question, sir. Can we use HMM for predicting virus data sets and upgrade it in the database? And how do we remove the redundancy in Markov model?
Can we use hidden Markov model for predicting virus data set? Can you please explain me what is all about? I think you can turn on your speaker and you can explain me what you want to know. I'm not able to understand your question. Now the second one is how do you remove redundancy using Markov model? See, first of all, Markov model, it is not a magic. You are you are constructing the model based on the system requirements. If redundancy is in your system requirements, definitely you'll have to model it. If you don't want to model the redundancy, you have to discard in your system requirements. So Markov model is basically modeling your system requirements only. It is not a magical thing like it is doing, but it is taking the model decisions. Okay, it based on the model, it is taking other decisions. So the redundancy and all, these are the architectural design which the system analyst have to take a call.
So here is the time to end the session, sir. So Lalit sir, you just shared your knowledge in the aspects of the software engineering and its reliability, networking, and using different data structures, and how the system's safety has to be decided by the mathematical modelings and different levels of PSA internal events, seismic PSAs, and you covered various topics in the system reliability analysis and component failure and how the data analysis has to be done. This all like we got a good information on that, sir. So who are new, definitely they are carrying a good knowledge from your session, sir. Thank you very much. We are honored to have your session. All the participants queries also you clarified on behalf of all the participants and IFTP program. Thanking you very much, sir.
Thank you, madam. Thank you.
Yeah, one second. Good afternoon, ma'am. Krishnavani, ma'am.
Yes, ma'am.
Ma'am, I have posted in the chat box. I hope you have seen. Whatever the material you have sent, ma'am, in the classroom, it is not available.
Okay, we'll be uploading one more time, ma'am, because we are slotting the data. So according to that, I'll post it one more time. No problem in that.
Okay, that is one thing. And one more email I have sent to ma'am. You kindly check.
Sure, definitely, I do that.
Okay. Thank you, sir. Thank you for the wonderful session. It was very, very informative.
And so the third week schedule is already posted in the WhatsApp groups. And tomorrow also we have the session with Vamsi Krishna, sir. So we have a schedule at 10 to 12 p.m. He is a business and intelligence specialist. So he is going to take the class. He is interested to take the class tomorrow. So I request all the participants to stay back tomorrow at 10 a.m. So we'll be continuing the session, 14th day of this IFDP program. Thanking you very much for your cooperation and patience listening. And every day you are very interestingly joining the sessions, listening to that and raising the queries, solving your problems. And I think you are at the back outcome carrying the knowledge. That is what we predicted as well. Thank you for joining. Bye bye.